Okay. Okay, now we start the theory of differentiation, chapter 3. In this chapter, we interpret derivatives as a slope and rate of changes. And also, we will estimate the derivatives of the functions, and also, we will calculate the derivatives of given functions. We will develop some rules for finding derivatives, which will make us to calculate the derivatives of polynomial, rational functions, and algebraic functions, and exponentials, and logarithmic functions, and trigonometric functions, and inverse trigonometric functions, etc. Okay? Some of those problems you are very familiar with, and but some of the functions that you may face for the first time, so we will touch those parts that you haven't studied before. These derivatives can be written in the world of velocity, density, or current, power, and temperature, etc. in physics, and also rate of reaction and compressibility in chemistry, and broad velocity gradient in biology, and marginal profit and marginal cost in economics, and rate of heat flow in geology are all means the same thing, which is the derivative. So derivative is a kind of a single concept to explain this such a diverse behaviors in many different disciplines. French mathematician Joseph Fourier told that mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. That's what he said to explain what is written there. You know the definition of derivative. Okay? The derivative of the function f with respect to x is defined as the formula f prime of x, which is the limit h goes to 0, then f of x plus h minus f of x over h when h approaches to 0. So if this limit does exist, then we call this function f this value is the derivative of f with respect to x. Okay. This definition can be defined when this right-hand limit does exist. When this exists, we write this one as f prime of x, and we call this is a derivative of f with respect to x. Okay, suppose we have a function g of x like this, then g prime of x, the derivative of g with respect to x, can be found from in this way from the definition. So, with the definition, we can write the g of x plus h and g of x like this, and find the limit of this function with 1 over h together, which is this. So we can say the limit, the derivative of this function g is this. These are the notations for the derivatives. There are many different ways of writing it, but they are all means the same. The symbol d and d over dx are called the differential operators. Differential operators. Okay, but they are all same. Okay, and the value of the derivative at a specific number a can be written in this way or this way. We call a function is differentiable if at a if f prime of a exists. Okay. You know differentiability implies continuity. 미가연적. You all know it. If it's differentiable, it's continuous. If it's continuous, then it's integrable. Okay. So if a function is f is differentiable at a, then f is also continuous at a. Okay. You can find the proof in anywhere. Okay. And you knows already the fact. So okay, proof that differentiability implies continuity. Here you will see easily that this limit, this equation means the limit is f of x is 0, which means f is continuous at x not. Okay. Okay, so there's exercises and I made some changes in the problems. So differentiate each of the following functions by the definition. Okay, then for this function, for constants, you can easily find the limit. The derivative is 0. If you have a linear function, the derivative is a constant number like this, and that's the same thing on here. And if you have the function with the exponent, then you may need to use the Lagrange the formulas to simplify the functions. But as you see here, the power of h's are there. The x minus x to the fourth can be deleted. So all terms has h's. So h can be simplified, and these are all goes to 0 when h goes to 0. It should be 0, not a. Okay. And then what? 4 to the 3 times x to the cube is left. So just this. So you must be familiar with it. Okay. You must find the derivative of this now by using the power rules. But if you have to use the definition of the derivative, then this is the way that you have to follow to have the solutions. Okay. And g of t, if it's a polynomial like this, then it's easy to have it. But the simplification makes this thing. So we will have the proof, the easier way of finding it. As you see, this is very tedious to do so. By using finding the derivatives by using the derivatives. If the function is simple, then it is very nice to do so. But if functions are getting complicated, then the computations are too tedious. So in the next section, we will find the easier way of finding the derivatives. Okay, and here the function is differentiable or not. Then all we have to do is just find the limit of it. As you see, this from the definition, this the values can be simplified this like this, and we knows this function approaches to 0 as when x tends to 0. Okay, so the limit exists, so it's differentiable, and the value is 0 at x is equal to 0. So we can find it. We can easily draw the graph to see the behavior of the function by Sage or others. Also, I expected you to discuss some geometrical and physical mean interpretation of the derivatives. I gave a short sentence on it, but you can still think more about with your background of your majors. Okay, that's the section 2.2, 3.1. Is there any questions?